When I was a small child, my dad once took us to this adventure camp where one of the main attractions was the Maut Kuan, also known as the Well of Death, where a couple of motorcycle riders would be driving on the inside of a well. Let us take a look at this video. So the motorcycle riders, they would start on the inside of a well from the bottom. They would start riding in circles and they would go up in velocity and they would start climbing on the walls, and they would reach a state in which they're driving on the inside surface of a wall. And I was quite puzzled to see this. It was entertaining and adventurous, of course, but first of all, how is this even possible? I mean, how is such a heavy motorcycle and a rider driving on the inside of a near vertical wall? And how are they not falling down? I didn't know much physics back then, but today I have the tools necessary to explain this problem. And it's an interesting problem. Not very complicated, very simple actually. And this is what we are going to discuss today, how the forces are balanced to even let this kind of a motion happen, where somebody is riding a motorcycle or a car on the inside surface of a near vertical wall. And what is the velocity necessary for sustaining this kind of a motion? These are the questions I'm going to answer today. So I have a couple of surfaces, a curved parabolic surface, a conical, spherical, cylindrical surfaces. The idea of the balancing of the forces is very simple. The only difference is a little bit of a calculations at the very end. So I'm going to do for all of these cases. First, let's focus on the balancing of the forces in the first case scenario. So here I have some kind of a curved surface. All right. This is the inside of a well, and the well walls have some kind of a curvature to it. Let's suppose this is a surface where if we have a z-axis, if this is the z-axis and this is the x-axis and this is the y-axis, then this surface may have some kind of a mathematical expression of, let's suppose z is equal to some constant a x square plus y square. All right. If this is the nature of the surface, I'll show how the equation for the surface will come into play later on. But what's important is this motorcycle rider is going round and round in circular trips in such a manner that its height is constant. Okay, so whatever the height is, its height is constant. Okay, and we are going to analyze the motion for round trip where the height of the rider is constant. So the problem is actually very simple. You see, first of all, if the rider is at a constant height, that means its radial distance is constant, its vertical height is constant. In that kind of a scenario, there must be forces which are balanced to create that kind of a system. So let's suppose I imagine the rider to be a point mass. Okay, we are imagining a very simple system of a point mass at this particular point. So let's suppose the rider is here. In that kind of a situation, what are the actual forces acting on the rider? So one of the obvious forces is the force due to gravity. Okay, so if the rider and the motorcycle has a combined weight of m, then the force due to gravity is going to be mg. And the second force is the normal reaction force, because if something is on top of a surface, due to the contact of that surface, a rider is experiencing some kind of a reaction force. You see, the gravity is trying to pull the rider down, but the surface is kind of blocking its way. So in that kind of a situation, the rider is going to experience some kind of a normal reaction force which is perpendicular to this surface. Okay, so if there is a normal reaction force which is perpendicular to this surface on which the rider is riding, then that force is, let's suppose, n. So from here, I can deduce what other forces must be involved. You see, n and mg are not exactly opposite to each other, but their components could balance each other out. So for example, if we look at the nature of the forces along the radial direction, because the rider is riding in a circle, all right, so we can think of this radial direction, where let's suppose the rider is riding at a radial distance of r, or in a circle having a radius r, then in the radial direction, if the radius remains constant, the forces must be balanced. So let us look at the forces in the radial direction. So in the radial direction, I can simply apply the Newton's second law, but in polar coordinates, right? So in polar coordinates, if the forces acting in the radial direction is Fr, then if you know the expression for acceleration in polar coordinates, AR is the radial acceleration, then this is nothing but AR is equal to R double dot minus R theta dot square. Now what is R double dot? R double dot is actually equal to 0 because it's a second order time derivative, and I'm saying that the radius is a constant as the rider is going at a constant height and a constant radius in the circular trajectory. So the first term comes out to be 0, and theta dot is nothing but what we say as omega, the angular velocity, where we can also apply the relationship of its speed v is equal to omega r being the radius of the circular trajectory. Now, what are the forces in the radial direction? So of course, the force in the radial direction could be the component of n. All right, so the normal reaction force may have a component in the inward direction. All right, and let's suppose if I define the angle, of this normal reaction force, let's suppose from the vertical to be theta, in that kind of a situation, this component of the normal force along the radial direction will be n sine theta. Right. So from here I can say that Fr is actually equal to minus n sine theta. Why minus? Because it is acting opposite to the radial direction. The radial direction is actually coming out of the center, but this is going inwards. So from here I can simply state that n sine theta is equal to minus mr theta dot square. Theta dot square can be written as mr omega square, and since v is equal to omega r, this can simply be written as minus mr omega square is equal to v square upon r square, or this can be further simplified as, let's suppose, n sine theta is equal to, the minus sign is not here, m v square upon r. Now this is an important equation, so I'm going to write down this as equation number 1. Now there is also another balance that is happening. The object or the rider is not changing in height. That means there must be a balance of forces in the vertical direction. So if we look at the balance of forces in the vertical direction, then again I can say that along the vertical direction, one of the forces is clearly mg, right? And the other force is the component of n along this particular direction, which is nothing but n cos theta. So along the vertical direction, if the height of the rider is not changing, that means this equation must be true. That is, n cos theta must be equal to mg. So here we have two distinct equations. Now let us understand something. From these two equations, I can explain why the rider is maintaining a constant height. I mean, how the force is being balanced. You see, when an object travels in a circular path, then there is something known as centrifugal force. So if you look at equation number 1, the right hand side, mv square upon r, this is a centrifugal force. This is not a force that arises due to some interaction, but rather this is a force that arises when objects are moving in circular trajectories. It arises as a result of the inertia of the system in a rotating frame of reference. This is actually known as a centrifugal force. Even though it's not resultant from some interaction, its effects are very much real. So whenever an object is going around in circular trajectory, it has a centrifugal force acting in the radially outward direction. And when something is moving with a particular velocity in a circular path, this centrifugal force leads to the normal reaction force, right? And this normal reaction force, if it is sufficient, it can balance the weight. Do you see it? When something is moving with a particular velocity, then it leads to centrifugal force, which results in some kind of a normal reaction. And a normal reaction force has a particular component in the vertical direction that balances the downward pulling weight. And it is this balance of the upward component of the normal reaction force and the downward weight that creates this situation where the rider can go on and on without changing its height. Now, of course, there may be a possibility of friction here. I have not included the friction term right now because the rider is driving a motorcycle and the wheels are rolling on the surface, and rolling friction is usually less. But in certain situations, the friction can be included in the equations. So from equation number 1 and 2, we can obtain this condition that will give us how much velocity this rider should be driving in to create the sufficient normal reaction to maintain a constant height. So we can say from equation number 1 and 2, if I divide equation 1 by equation 2, so let's suppose if I say n sine theta is equal to and cos theta, this simply becomes mv square upon r. R here is of course the radius of the circular trajectory of the rider, okay, and divided by mg. So this simply becomes m and m gets cancelled, and we are left with n and n also gets cancelled, and we are left with tan theta is equal to v square upon rg. So here we have it, the condition for what should be the velocity of the motorcycle to maintain a constant height as it keeps riding on the inside of a well. As you can see, g here is a constant, r depends on the radius of the circular trajectory, theta depends upon the slope of the surface. So theta will give us an idea about what is the nature of the surface, and v of course is the velocity of the motorcycle rider. And to appreciate how this can be different for various cases, I have 4 different scenarios in front. So here are 4 different possibilities of how the well of death can be constructed. It could be a conical surface, it could be some kind of a parabolic surface, it could be some kind of the inside of a spherical surface, it could be a cylindrical surface. So I'm going to show how we can apply this particular equation, because right now this equation does not consider what is the nature of the surface, and the nature of the surface will just mainly be included in this particular term tan theta. You see, the tan theta basically gives you an idea about if you draw a perpendicular to the surface, because the normal force is in a perpendicular direction, then the angle that it makes with the vertical. So I can give you a little bit of a better idea of what tan theta represents. If you draw a tangent to this particular surface at the point in which the rider is riding, then as it turns out, this tangent is at a slope of angle theta. You see, the tangent is perpendicular to the normal reaction force, so it's 90 degrees, and the vertical is at an angle of theta. So clearly this angle is nothing but 90 degrees minus theta, right? And if this is 90 degrees minus theta, n cos theta and r are at perpendiculars, so that means this angle must be theta itself. So from the geometrical construction, we can see that the theta that we have defined earlier, that means the normal reaction force being at an angle theta with the vertical, is the same as the slope of the tangent of the surface at that particular point. Now, what is the slope of the particular tangent of the surface at that particular point depends upon the detailed nature of the surface. So if we look at this particular surface, let's suppose we take the case number 2. So here the slope of the surface at this particular point is basically given by tan theta, right? This is tan theta, and we know that tan theta is simply equal to v square upon rg, where r is the radius of this circular trajectory, g is the acceleration due to gravity. Now let's suppose that I say this is the z axis, this is the x axis, and this is the y axis. Then tan theta is simply the slope at this particular point. So if I'm interested in finding the slope of the surface at this particular point, what I can do is I can take a gradient of let's suppose dz upon dx at this particular point on the xz plane. So the slope is simply dz upon dx, which is nothing but equal to tan theta, right? Now this theta is the same for every single point as the rider is riding on the circular trajectory. So the theta must be same because of symmetry of this particular surface. However, I can calculate what this tan theta is for one particular point. So let's suppose I choose a particular point on the xz plane. So this is the xz plane that you have here. On this particular plane, I can figure out what is the value of tan theta by simply finding out what is dz upon dx. So tan theta in the xz plane, if I'm only interested in the xz plane, because I'm only interested in figuring out what is the value of theta, then this is nothing but d upon dx of what is z. I said z has some kind of a parabolic surface equation. Z is equal to a is a constant, x square plus y square, and this is simply equal to a x square plus y square. Now because this is the xz plane, in the xz plane y has a value of 0, so therefore this simply comes out to be tan theta is equal to twice ax. So if I substitute this particular expression here, then this simply becomes that twice ax is equal to v square rg, where r is nothing but x here because we are considering the plane x z plane. So r is just simply equal to x. The r is just equal to x here, and this is just a technique of finding out what the slope is. All right, because I'm considering only the x z plane. In that kind of a situation, v square is simply equal to twice ax square. So what is the ax square in the xz plane? Ax square is nothing but z, right? So this is nothing but, there must be a g here, twice zg, where z simply represents the height, this particular height at which the rider is in equilibrium. All right, so if I write z as h, this simply becomes v square is equal to 2gh, or finally v must be equal to root over 2gh. So we have obtained this important criteria that the velocity with which the rider is riding must be equal to root over twice the acceleration due to gravity multiplied by the height, so as to maintain a particular equilibrium in which the height of the rider does not change. It is driving in a circle, but it is maintaining a constant height from the ground. And if this condition is satisfied, then they will be able to establish it. So without the particular velocity, this condition will not be satisfied. Now let us look at the other surfaces. One of them is this conical surface. Again, we will use the same expression which we have obtained here. This particular expression we are going to use, that is tan theta is equal to v square upon rg. However, what is tan theta here? Tan theta is the slope of the surface at this particular point, right? The slope of the surface at this particular point is given by tan theta, which we can decide what they are based on, let's suppose this is the height h and this is the radius r of the circular trajectory. So in that case, theta is this. All right, so what is tan theta in this conical surface? Tan theta is simply equal to h upon r, which is equal to v square upon rg, where r and r simply gets cancelled in both sides, and finally we end up getting velocity square is equal to rg, or hg, so v is equal to root over gh. So for the conical surface, if the well was structured as a cone, in that case, the velocity that the rider must maintain must be equal to root over gh if it is planning to maintain a constant height. All right. Now, if we talk about other surfaces, like let's suppose the spherical surface. So let's suppose the rider is riding on the inside of a spherical surface where the surface has a slope given by theta in this particular manner. And let's suppose in the spherical surface, the radius of the sphere is actually given by capital R, and the radius of the circular trajectory is given by small r. Now, in the case of the spherical surface, it's a little bit better to visualize the expression in terms of the, radius of the sphere and the theta instead of the height. So what was theta here? As I explained earlier, theta was the angle made by this r, capital R vector with the vertical axis, which is the same as the angle subtended by the radius of the sphere with the vertical axis, right? So here, if I again apply the formula, that is tan theta is equal to v square upon rg, then tan theta can simply be written as sine theta upon cos theta is equal to v square upon rg. Here, from the geometry of the setup, we can see that capital R sine theta is equal to small r, right? So capital R sine theta is equal to small r. From here, I can say that sine theta is equal to small r upon capital R. So if I apply this here, this expression simply becomes, if sine theta is equal to small r upon capital R, then this is small r upon capital R cos theta is equal to v square upon rg. So from here, what do we get? From here, we get that v square is equal to small r square g upon capital R cos theta. So here, of course, the capital R is the radius of the sphere and small r is the radius of the circular trajectory of the rider. And this gives us the condition for the equilibrium maintained by the rider. Now, again, in the case of the cylinder, however, if let's suppose the rider is on the cylinder somewhere here, let's suppose, and it is creating some kind of circular trajectory. Now, as you can see, the balance of the forces will not be maintained in the case of a cylinder. Here, the balance of the forces was maintained because there was a normal reaction and the component of the normal reaction was balancing the weight. If you look in the case of a cylinder, the component of the normal reaction is perpendicular to the surface, and the weight is actually in the downward direction, which is mg. So in that kind of a situation, the component of the normal reaction in the direction opposite to mg is actually 0. So the only way that this kind of a motion on the inside surface of a cylindrical well is sustained is if there is friction involved. You see, in the other cases, I did not include friction because it's a little bit less compared to the other forces involved. But of course, friction does play a role. And if friction is involved, and I say that there is a friction F against the sliding motion of the surface downwards, that in that kind of a situation, the outward radial force is again going to be equal to mv square upon r being the radius, right? So mv square upon r, this gives us an idea about what is the centrifugal force. So the only way in the case of a cylindrical well, this kind of a motion can be sustained is if the force of friction is equal to the weight. Now, what is the force of friction? The force of friction is given by the coefficient of friction and the normal reaction force. Now, the normal reaction force arises due to the centrifugal force, right? So N is equal to mu mv square upon r is equal to mg. Here, if I cancel out m on both sides of the equation, then this will give me an expression v square is equal to capital Rg upon mu. So if friction is involved in that kind of a situation, on a cylindrical well also, this kind of a motion is possible. So as you can see, based on various different surfaces, the conditions necessary to sustain this kind of motion may be slightly different, but at the end of the day, the motion is only possible because there is something preventing the weight from pulling the object downwards, whether that is the component of the normal reaction force and a combination of the friction. That depends upon the details of the scenario. So that is how this kind of a motion is possible, you see. So for various circumstances, this motion is possible due to the balance of forces along the radial as well as along the vertical axis. And as long as the forces are balanced and along the vertical axis, along the radial axis, the rider will go on in circular trajectory at a particular height. And of course, the rider needs to have guts to actually do this kind of motion. All right, so that was the interesting problem of the well of death physics problem. So I hope you learned something from it. You enjoyed the video. I'll see you in the next one. Thank you very much.